Okay, Assalamualaikum warahmatullahi wabarakatuh. Today we will continue our topics with the bending of members made of several materials, or we can call it composite beams. So previously we have had look into material comprised of one material only with a similar modulus Young. Here we can call it the bending stress in composite beams. So when we consider a composite beam that comprise of two material 1 and material 2. So this is the neutral axis at the center of material. So for the central part, the strain distribution normally coincide the parts, whereby the strain max normally exists at the material on the top side, whereby the y reach the maximum value. Okay, so these two material have two different modulus Young, representing each modulus Young. E1 for material 1 and E2 for material 2. So normal strain, when we talk about strain, so normal strain usually varies linearly. Okay, so from the center it should increase, the strain should be increased up to the maximum value of y. So in this case, the Ex equal to negative y rho, as previously discussed in a previous section. So when we talk about normal strain, it happens to the normal stress. It should also varies linearly. So sigma y equal to Ey strain x equal to negative Ey over rho. So however, in this composite beam, it does not only have one E1, but it also has the E2. So there are two equations behave for a single strain. Okay, so this comes the conflict because why? The neutral axis does not pass through the section centroid. Okay, so it may be similar but maybe not similar. If I can show the figure, Okay, this might be the foundation. These are the part. So for material 1, it behaves something like this. Okay, but for material 2, it behave differently. So can you see, previously we have almost similar due to one material properties only, but for composite plate it has two stress distribution. So this conflict due to the neutral axis does not pass through the section centroid of the section. So how are we going to solve? Okay, so there are few steps. There are not call it steps, but it is advised to follow the following procedure. So we can call it a procedure. So first we have to transform the bar to an equivalent cross section made of only one material. So meaning that if you have steel and brass, you have to convert, to transform to either steel or brass. So this is the first procedure. So you can use the n equal to E1 to E2. So this I will explain later. Okay, that is the procedure number 1. So number 2, so you can evaluate the cross sectional properties of the transform section. Third one, you can calculate the maximum stress of that particular one material. Finally, you calculate the other material by converting or multiplying the ratio of E modulus. Okay, for example, okay, this is the cross section at the natural This is material 1 made of steel. This is material 2 made of brass. So the first you should do is to transform. The first is to transform either I should use different. Okay, this is all brass, or all steel. The the E for steel normally is higher than brass. So no wonder if you are converting the steel into the brass, the steel into the brass, you can see the size shrinkage a bit. Okay. Oh, I should draw a proper dimension then. Okay, this is you fix A, this is A, this is B. So when you fix all brass, the steel shrinkage, or if you fit the B, the A will shrinkage. So this is to ensure that all respective E's are followed. So how can we change into the ratio? By using the transformation ratio N, representing the E2 and E1. So how can you set E1 and E2 on the top side of the bottom side? The trick is something like this. If you are using this E2 on the top side, E1 in the bottom side, you are I call it transforming material 2 into 1. So final is fully 1. In contrast, if you are using an E1 into E2, okay, or I should use the 1 2 into the brass and steel. Okay, let's say 1 is brass, 2 is steel. Okay, 1 for brass, 2 2 for steel. Okay, meaning that for this case you are transforming brass into fully steel. Okay, for the top side, and E steel to E brass, meaning that you are transforming steel into fully brass. Okay, so how does the size make an significant change? Okay, let's say we have example. We have a pair of material. This is brass, steel, brass. The height is 75. The width 10 mm. This one 18. And this one also 10. So we have black and orange. So how can we transform? By using the N. So what are you trying to do? You are trying to transform the brass into the steel, or the steel into the brass. Okay, let's say we are transforming, first we are transforming into fully brass. So N should be the E steel over E brass. So sorry, the E for steel is 200 gigapascal. E for brass is 100 gigapascal. So we are converting into fully brass. So brass should be at the lower side. So equivalent to 200 over 100 equal to 2 times. Okay, what is the meaning of 2 times? The meaning that the original E, okay, meaning that this is the original brass, okay, but the steel is converting from steel into brass by multiplying the original length into the ratio, so which is about 36 mm. Okay, so you are no longer steel, they are fully brass. Okay, for comparison, if we are transforming into fully steel. So N is E brass into E steel, equivalent to 100 over 200, equivalent to 0.5, meaning that the size of steel that transform into steel is half. So we have original S, which is 18, but the value of the steel converted from brass is half of its width, which is 5 only. So the total length is about 28 full steel. Here 10, 20, 56 of full brass. Okay, then we can continue with the what we call it, the identification of sigma, the M, the Y, the I, the BH3, okay, by calculating the respective shape. Okay.